everyone, welcome back to Markov processes. When we last left off, we were talking about stationary distributions. In this video, I want to wrap up sort of the intro to stationary distributions. This certainly is not going to be the last time we talk about them. We'll probably mention them in every video from now until the end of the course. But I do want to wrap up sort of the initial discussion and move on to the next topic. Now, this wrap up is going to be very short. So this video is going to be very short. Now, if you're looking below at the timeline, you might see actually quite a long video. I'm not sure how long it's going to end up. It might even be longer than usual. But what I want to say to you, very short, and I'm going to invite you to exit the video at several points. Of course, you can come and go whenever you want. I can't make you watch this or exit it. But most of this video is going to be about proving the pi1 and pi2 theorems. And in fact, we're not going to make it all the way through that. This is long, tedious stuff that will go into the next video as well. I don't think a lot of you are going to want to watch these theorems. They are, again, as I said, tedious, and I don't think they teach you anything that you need to know. For example, in some previous proofs, I wrote the number of hits on a state as a sum of indicators, where I indicated, did I hit the state at time 1? Yes or no, 1 or 0. Did I hit it at time 2? Yes or no. And that was a pretty cool tool to take away from that proof. So even if you didn't care about that proof, you had a new tool about counting hits on states as sums of indicators. For these proofs, I don't think this is the case at all. I think they are tedious and they will zap your desire to be here and learn more about Markov chains. I think they will slow you down and sort of make you not want to come back. And I hope you'll come back. So let me get the stuff I need to say to you out of the way, and then I'll head into the proofs and I'll let you know that's a good exit point. And then even then, if you stay, I'll give you a couple of other good exit points as well. As I said, we've been talking about the stationary distribution. So I want to let pi denote the stationary distribution. Remember, that's like our name for the distribution. If I say pi sub I, that's a specific probability from the distribution pi. And if I say pi with a vector over it, this is a row vector filled with those probabilities. The stationary equation looks like this. Pi j is the sum over all I in the state space of pi I pij. This is something that needs to hold for every j in the state space of the chain. Let's focus in on the summand over here. The pij, for a fixed j, as I runs over the sum, the pij's are running down the jth column of the transition probability matrix, that bold double-lined p. And as the i's run over the sum, these pi i's are running across the row vector that we're calling pi with a vector on it. Across a row vector, down a column, multiplying individual entries and adding them, that is vector matrix multiplication. In fact, this right-hand side here is the jth entry of the pi vector times the transition probability matrix. This left side is the jth entry of the pi vector. So what you're seeing here, even though it's for a particular j, it holds for all j. And if you want to get that all into one statement, we can write this as the vector of pi's is equal to the vector of pi's times the transition probability matrix. Be warned that if you're looking at other sources, if they are Markov sources or probability sources, likely this is how it's going to look. But when people use Markov chains in other areas and maybe teach about them for other areas like AI or something like that, people who are not sort of central in probability and Markov chains I shouldn't say tend, but there's a chance that their transition probability matrix is going to be the transpose of what I'm using. And in that case, the pi vector might be a column vector. And so this might go the other way. You might see this pi and this p interchanged, but I'm definitely leaving it the way I have it. That's definitely the way I want it. So what are we looking at here? This kind of looks like an equation like this, which you might recall from linear algebra. So here A is some matrix, V is a column vector, and lambda is a scalar. And this is an eigenvalue-eigenvector relationship. In this equation, V is an eigenvector for the matrix A, and lambda is an associated eigenvalue. If you go back up here, yes, things are multiplied in a different order, but what we're seeing is that the pi vector is an eigenvector of the transition probability matrix associated with an eigenvalue of 1. And if you want to get technical, because it's backwards from maybe how you've usually seen eigenvectors and eigenvalues, we say that pi is a left eigenvector of the transition probability matrix. Now, people who use the transpose of the matrix won't have that. You'll see a more traditional right eigenvector. But in terms of eigenvalues, the eigenvalues of a matrix and its transpose are the same. That's not going to change the eigenvalues for a matrix. So I want to briefly talk about something known as the Perron-Frobenius theorem, or actually a much bigger body of work by those two guys, known, I'm going to call it Perron-Frobenius theory. And Perron-Frobenius theory actually is not centered around stochastic anything, and certainly not Markov chains. So they start with just a matrix, usually something known as a regular matrix, and depending on what you're studying, actually the definition of a regular matrix could mean something different. I don't even want to go into it. It's not our concern here, but it gives lots of results about regular matrices defined as they define regular matrices. And within Perron-Frobenius theory, there are results about stochastic matrices. Now, a stochastic matrix is any matrix where the rows sum to 1, as ours do here, and maybe someone would say column sum to 1 if they're using the transpose. And a result within Perron-Frobenius theory says that any finite number of rows and columns, stochastic matrix will have at least one eigenvalue equal to 1. Furthermore, it says that the magnitude of the eigenvalues, if you look at the magnitude, because you may have positives and negatives, but if you take the absolute value of all of the eigenvalues, they are all less than or equal to 1. So not only is there going to be an eigenvalue of 1, but it's going to be the maximum eigenvalue, whether you take the absolute values or not. It's going to be the maximum value. And what does this mean for us? We definitely have stochastic matrices. This for us means that if our stochastic matrix is in fact a transition probability matrix associated with a Markov chain on a finite state space, mind you, we will have at least one stationary distribution, because the associated eigenvector to that eigenvalue 1 is going to be our pi. Even if you find an eigenvector associated with the eigenvalue 1 for the transition probability matrix, and you're not getting numbers that sum to 1, you could renormalize it so that it does sum to 1, and that would be a stationary vector pi. So what we have just learned from Perron-Frobenius theory, which I'm definitely not going to go into, that is a huge aside, I mean, that could be its own course, is that if you have a finite state space for your Markov chain, you will always have at least one stationary distribution. You may recall from when you took linear algebra and learned about eigenvectors and eigenvalues, about multiplicity. So if you have an eigenvalue of 1 with multiplicity, say 2, then you would have 2 associated eigenvectors, which could be renormalized so that they sum to 1, and that would correspond to 2 stationary distributions. And there was not a lot of setup here. So in theorem pi 2 that I've given you, I gave you some sufficient but not necessary conditions to have a stationary distribution. And this is less conditions, or different conditions, if you will, because theorem pi 2 did not require a finite state space. But yes, we now have a new sufficient condition for existence of a stationary distribution, not uniqueness and not anything more about it that we will talk about today, because I'm going to finish out theorem pi 2. I will prove theorem pi 2, even though I'm not proving the more general Perron-Frobenius result. So let's talk about my theorem pi 2, because when I gave it to you, I said it was partial theorem pi 2. I didn't state the whole theorem because I didn't want to sort of lose the forest for the trees and make it too messy up front. Theorem pi 2 so far said that if you have an irreducible and positive recurrent Markov chain, even an infinite state space, that a stationary distribution exists and is unique, and more. And I want to fill in the and more right now to fully state theorem pi 2 for this course. So let's let xn with brackets be an irreducible Markov chain on a discrete state space S. Remember brackets unless you're talking about a single random variable at time n. So suppose that starting at state I, you expect, because you've computed it somehow, and we're going to get to that, but suppose starting at I, you expect to return to I in, say, 8 steps. once you have returned to I by the Markov property, what happens next does not depend on how you got to I. So you are at I again, in essence, starting over using the Markov property. So you still expect to return to I in 8 steps. And once you're back, you're starting over in essentially in the Markov, using the Markov property, you expect to return in 8 steps again. Now, let's use some formal notation for this. I am going to use a capital E for expectation sub I. Now, I think I've already given you this notation. I certainly have for probabilities back in lecture 5 or video 5. But when I put a subscript here, it's going to represent the starting value for the chain. So I'm going to define capital E for expectation sub I, representing that the chain is starting in state I, of T sub I. Now, this is going to be the first return time to state I. I'll write that down in a moment. But again, this is the expected value of T sub I, given that we start the chain at I. And we're supposing right now for this example that this number is 8. And T sub I is going to be the first return time to state I. So the minimum over n greater than or equal to 1, not including 0, because we want to move in order to try to return. The first time at times greater than or equal to 1, where we hit state I. And this is not a return time unless you are in this context where x0 equals I. So starting from I, in this example, we expect to return to I in 8 steps, or on average, every 8 steps, right? Expectation is an average, is a probability weighted average. This doesn't mean we're going to be at I every 8 steps. But if we expect to return on average every 8 steps, this means that in the long run, if you start at I, you expect to return 8 steps, you expect to return again in 8 steps, you expect to return again, and you will find yourself in state I approximately 1/8 of the time. A long run probability. This is like a limit or even like a stationary distribution. If you're in there 1/8 of the time, then you will continue to be there 1/8 of the time in the long run. It's sort of limiting and also stationary at the same time. So what if you do not start your chain at state I? By irreducibility, which was part of my setup here, you will eventually hit state I. And if you have positive recurrence, boy, you'll come around and you'll move around a lot faster. You will eventually hit state I just by irreducibility alone. And once you do, you will continue to return on average in 8 steps. So in the long run, you will find yourself in state I 1/8 of the time. This is the idea between the final statement that will conclude or finish out my theorem pi 2. Here it is. For an irreducible positive recurrent Markov chain, a stationary distribution, number 1, exists, number 2 is unique, and it satisfies this equation. The probability you find the chain in state I is actually 1 over this expected return time. So this is like your 8, and this is your 1/8. And this is the full theorem pi 2, and this is going to hold for every I in the state space if you have irreducibility and positive recurrence. So not only will we have existence and uniqueness, but we'll have an idea about what these probabilities look like. As a quick reminder, theorem pi 1 was about limiting distributions. It said if we have something irreducible, positive recurrent, and aperiodic, then if we look at the probability of moving from I to j in n steps and let n run off to infinity, this limit is going to exist and be independent of I. Here is your first exit point of this video. In the remainder of this video, I'm going to set off to prove both of these theorems. This is going to take a while. We're definitely not going to finish within this video. And as I said, it's kind of tedious. So if you want to leave now, I wholeheartedly support your decision. The next new topic, because I'm going to need another video to finish these proofs, but the next new topic is really, really cool. So I hope you come back. That's going to be about first step analysis for Markov chains. It's a super powerful, super fun technique for doing amazing computations. You can really impress your friends with this, your roommates. It's really, you must come back for that. But if this is it for you for today, I'll see you in the next one. But if you want to stay for the beginnings of these proofs, let's do it. The first one I'd like to consider is theorem pi 2. I actually want to prove theorem pi 1 first, but theorem pi 2, at least part of it, is going to help me prove theorem pi 1. So what part? I am just going to prove this part of the result. I'm going to say if we have something irreducible and positive recurrent, a stationary distribution exists. I don't care about uniqueness yet. I don't care about this result yet, because going back to theorem pi 1, where I want to show a limiting distribution exists, for theorem pi 1, I do have irreducibility and positive recurrence. So if I can prove this right here, then I can say when proving theorem pi 1 that a stationary distribution exists. And I'm going to use that to help me prove that statement about limits that we had in theorem pi 1. So let's try to prove existence right now. This proof isn't actually that bad, but as we go on today, they're going to get worse and worse. And I keep saying tedious for short. Let's prove existence when we have irreducibility and positive recurrence. I'm going to start out by fixing any starting state for my Markov chain. I'm going to call it, say, K. And then I want to count, starting at K, I'm going to go until we first return to K. And along the way, I want to count the expected number of hits on a state I. I could be different from K. I could equal K. And if I equals K, I don't want to count the first hit, but I will count the second hit where we're stopping the chain. Let me show you what I mean. So here is some level K, some state K, and I'm going to imagine a sample path running along until we first return to state K. So this doesn't mean that we haven't crossed K, by the way. I'm just not drawing it that way, because if I cross over K, you might think we've hit K. If I made a more detailed picture, we would just have line segments. I move to this state, I move to this state, right? So starting at K, you might move to K plus 3 and then K minus 10. You're not hitting K, you're crossing it. And in my sloppy picture like this, crossing it might have looked like a hit. That's why I'm keeping this sample path above K, because I'm not showing you those individual steps. And I didn't want it to look like I hit K in here. But let's mark off a state I here and look at its level. Now in this picture, starting from K and returning to K along the way, how many times did we hit state I? In this picture, 4 times. But the next time you run a sample path, it's going to be different. There's randomness here. I want the expected number of hits on state I in this path from K back to K. By the way, if I equals K, we are going to define things here so that we're not counting our starting at K, but we are counting landing at K. And so if we're starting at K and going until we return to K and counting the expected number of hits on K, but not allowing that count at time 0, that expectation is always going to be 1. We're always going to be counting this hit on K right here and ignoring the starting value. So let's set up some notation. An expected number, let's use a mu for mean. The expected number of hits on state I might call mu sub I. And let's formalize what we've just been talking about. So I'm going to let tk be the first time at times greater than or equal to 1 for the chain to hit state K. I want to not stop at 0. I don't want to say I've started at K, so I'm stopping at 0. I do want to allow it to run. So n is going to be greater than or equal to 1 here. And if we start at K in that context, this is a first return time. The mu I is the expected number of hits on state I before or up to and including when we hit K. We can write it as the expected value of the sum as n goes from 1 to tk of the indicator that indicates whether or not at time n we are hitting I, all in the context of starting at state K. So let's see what we can do with this expression. The first thing I'm going to do is just maybe make it a little cleaner by taking this initial information and using our subscript notation. So I'm going to write this as the expected value with a sub K and then just write this. This means exactly the same thing as the line above. This is notation for this. And then I want to pull this sum outside of the expectation. The expectation is averaging out the randomness, but this is random and this is random. So I can't pull this sum outside because it involves a random variable. So I'm going to do a trick that, maybe I should have told people to look out for. I did say there was nothing new to learn from these proofs that can help you in other situations. I guess I lied. Here's one, but I promise the rest of it's super tedious, not something you want to see. To get this sum outside of the expectation, I'm going to rewrite this as the sum as n goes from 1 to infinity. And then I'm going to change the indicator to be the indicator that xn equals I, comma, and just like in probability, that n is less than or equal to tk. So whenever n gets above tk, this indicator is going to be 0 and 0 for all time for all larger n, in effect cutting off the sum. Now I can pull the sum out of the expectation. There's nothing random there. And I've got the expected value of an indicator. And we do know from lesson 6, I believe, that the expected value of an indicator is always the probability of the event being indicated. So here is an expression for mu I, the expected number of hits on state I between 2 successive visits to state k. So I want to play with this sum a little bit. So as an aside, let's look in the context, in the condition where we're starting the chain at k. I claim that this sum is equal to the same sum with the n subscript replaced by n minus 1. If you'd like to rewrite this as an x sub n, but instead let n in your sum go from 0 to tk minus 1, you certainly can do that. I think I'll just leave it like this. I want to convince you that these are the same, not in general, but in this context, in the universe where x0 equals k. So let's look at first the case where I equals k. And I'm going to take this left-hand side here. If I equals k, I can replace this I with a k. And now what is this sum? I'm starting from time 1 and going up to time tk and counting the hits on k. But from time 1 up to tk, I'm only going to hit k one time, and that is at that stopping time, t sub k. So this sum is 1. It's going to be a lot of zeros and 1, and that 1 is going to happen at the very end of that sample path. Let's look at this side of this equation. And because I'm in the case where I equals k, I'm going to plug in k. And again, you could re-index this and call this x sub n. But effectively what's happening here is we are introducing an indicator at time 0, and we're removing the indicator at time tk. So counting hits on k, this is also going to be 1. This is going to count the first hit on k. The very first indicator in this sum is 1, and the rest are 0. So this left-hand side right here is 1. This right-hand side right here is 1. The left-hand side is equal to the right-hand side, at least in the case where I equals k. So now let's do the case where I is not equal to k. Let's look at the terms I have over here as compared to this sum. I put in an additional term here, and that is the indicator for x0, but I took out a term, and that is the indicator for x at time tk. Because we start this chain at state k, and because I is specifically not equal to k here, the indicator that I included in this sum that was not over here, the indicator that says x0 equals I, that's always 0, right? Because at time 0, we are definitely at state k, and this indicator, when n is 1, is the indicator that x0 equals I, and I is not k, so that indicator is always 0. So no one cares that I introduced an indicator into the sum. On the other hand, not only did I introduce an indicator into the sum, but I peeled one off the other end, and let's see why that doesn't matter. X at time tk is always k. So the indicator over here, when n equals tk, which is missing from this sum, is the indicator that x at time tk is equal to I. Now x at time tk is always k, I is not k. So the final indicator here in the case when I is not equal to k is always 0. So it doesn't matter that I peeled it off and didn't include it in this sum. So again, by shifting these indices, this sum has an indicator at time 0 that this one did not have, but it doesn't matter that I included it because that indicator is 0. This one is missing an indicator that this has. It doesn't matter because that indicator is also 0. So hopefully I've convinced you that this is equal to this, where I is either equal to k or not equal to k. So let's go back to our definition of mu I. Mu I was defined to be this expectation, and we showed that that's equal to this probability. Similarly, we can say that in this context, it's okay if I replace this n with an n minus 1. So mu I, as long as we're in the conditional universe where x0 equals k, can also be written in this way. And by very similar steps to what we did when we showed this was equal to this, we can show that this is equal to this sum of probabilities. So at this point, I'd like to invite you to pause this video and write down these two expressions for mu I, because in what's coming up, I'm going to suddenly claim, and here's mu again, here's mu I, here's mu J, and it would be really helpful for you to be able to see that quickly and believe it because you have these expressions written down in front of you somewhere. But with that, I have a most amazing claim for you. And that is that mu j is going to be the sum over all I in the state space of mu I times pij. And this looks just like a stationary equation. Now, I'm not saying the mu i's form a stationary distribution because they are most definitely not probabilities. They are expected return times to state I or state j, depending on what subscript we're using. And that's going to be at least one time step to return. By the way, they are expectations. So the mu's are not going to be integer valued. They are averages, right? Average return times, probability weighted averages. So they're not going to be integer valued, but they are certainly going to be greater than or equal to 1. Why do I care about this claim? I care about it because it looks an awful lot like a stationary distribution equation. And if you were to make a row vector out of the mu's, like I'll call it mu with a vector over it, this appears to be a stationary vector of some sort and would in fact be a stationary distribution filled with probabilities if we took all of the mu's, added them, and then divided all the mu's by that number to normalize them to make them all be between 0 and 1. So let's prove the claim, and then let's talk about that normalization. I'm going to start with the right-hand side, the sum over all I in the state space of mu I pij. Now, one of my expressions for mu I looked like this. I'm just going to plug that in. That's one of those things I asked you to write down. And now I'm going to pull the pij into this inner sum with the n's because there's no n. It doesn't matter. It can be inside or outside. And I'm also going to interchange the order of summation. What I'm going to do next is something I don't like doing. I don't like pulling a magic equation out of the air, especially when I'm teaching. But I'm going to start with a different expression and show you it's equal to this so I can plug it in here. I prefer to start here and build out the different expression, but that's going to be a lot harder and take a lot more time. So I'd ask you to bear with me as I pull a magic expression out of the air that kind of looks like this summand. And we're going to take some steps and show that it's equal to this summand. And then I'm going to come back to this slide and replace this summand with the new magic expression. So I'd like you to consider the probability starting from k that xn is j, xn minus 1 is I, and n is less than or equal to tk. This is the summand that I had on the previous slide without the xn equals j and without the pij at the end. This, of course, this subscript k is saying that we're conditioning on the chain being at time 0 in state k. But recall at the beginning of the course, when we talked about unraveling the definition of conditional probability, we would write the probability of A intersect B as the probability of A given B times the probability of B. That's exactly what I want to do right now. I'm going to let this be event A and this be event B. I'm going to do that unravel, all while staying in the conditional universe where we start the chain at k. In other words, I'm going to have sub k on all my probabilities. So we get the probability starting at k that xn equals j, given that xn minus 1 is I and n is less than or equal to tk, times the probability starting at k that xn minus 1 equals I and n is less than or equal to tk. This again, of course, is saying that xn equals k. And what is this saying? If the first return time to state k is at times greater than or equal to n, then I know for sure I was not at state k at, say, time 1 or time 2 or time 3 or anywhere up to time n minus 1. I was not at k. I could have been at k at time n. I don't know that for sure. I just know that it's going to be at time n or larger. So again, if the return time to k is greater than or equal to n, that tells me for sure that all the x's up to time and including time n minus 1 are not k. On the other hand, if I know that all the x's up to and including time n minus 1 are not k, then I do know that the first return time to k did not happen until a time greater than or equal to n. In other words, this event is equivalent to this event. So I'm not going to take the time to write another line or mess up my slide any more than it needs to be. But we could rewrite this entire probability. We can replace this with this, and we could put this k back into the probability. If you like that better, we could have a comma, x0 equals k. But look at what we have. We've got the probability that xn equals j given xn minus 1 equals I, and then a bunch of stuff that happened before time n minus 1. But once you know where you are at time n minus 1 by the Markov property, none of this, including this, matters. I'm going to drop it all. I'm going to write this as the probability that xn equals j given xn minus 1 equals I. Not only did I drop this, but I dropped this because I no longer care that the chain was started in state k at time 0. And I'm just going to bring this down. Now this over here is a one-step transition probability, lowercase p sub ij. So what we have, I'm going to write it in the reverse order, is this. And this was the summand on the previous slide. I stopped a calculation with a double sum of something that looked like this. And now I'm going to replace that summand with this. So let's get back to it. Here's where we were. I'm going to replace all of this with our new expression. And let's look at this sum over I. There's only one place an I appears here, and that is right here. Nowhere else. So if you sum over I, you are marginalizing out this random variable, and you end up with, the sum goes away, right? You summed it out. You end up with the sum as n goes from 1 to infinity of the probability starting from k that xn equals j and n is less than or equal to tk. And if you wrote that down, you would recognize this as mu sub j. From here to here, this was the claim. This was what I wanted to show, to claim that the mu's are they're satisfying the stationary equation, but they're kind of forming a stationary distribution if they were probabilities. At least they satisfy the stationary equation. The whole point of this proof was to show existence of a stationary distribution, and this is going to be the base for that. So to finish, I need to divide both sides of this equation, in effect dividing this and this by something, to normalize these mu's so that they are probabilities that sum to 1. I'm going to define pi sub I to be mu sub I divided by the sum of all the mu's in the state space. And that would be it. Assuming we can get this sum, assuming this sum converges, because if it diverges, if it's infinite, then this normalization step is not going to make any sense. Mu j is the expected number of visits to state j between 2 consecutive visits to state k. Let me make this really concrete. Suppose your state space is just finite with 5 states, 1, 2, 3, 4, 5. And let's say the magic state k is state 3. So I'm going to start at 3 and I'm going to go until I return to 3. And I want to know let's look at what happened in between. We've got mu1, it's going to be the expected number of visits to state 1. In that interim where I start at 3 and end at 3, we've got mu2, the expected number of visits to state 2. We have mu3, which is always defined to be 1. If you start at 3 and end at 3 and you don't count at what happens at time 0, then you will count exactly 1 visit to state 3, and that will be at that termination. So mu3 is 1. Mu4 is the expected number of visits to state 4, same for mu5. If you sum all of those, if you say, starting at 3 and ending at 3, I expect to visit state 1 8 times, and I expect to visit state 2 5 times, and if you add those up, that's going to be where you are between 3 and 3. That's going to give you the expected number of steps to return to state 3. So if we sum over all j, and I'm going to include the special state k or state 3 in my example, that will just add a 1 into this sum. But the rest of the terms, that sum will represent the expected return time starting from state k or state 3 and returning. This is finite because my chain for this theorem was positive recurrent. The expected number of steps it takes to return to a state, given that you start at the state, is always finite for positive recurrent states. And for a positive recurrent chain, all the states are positive recurrent. So we're done. This sum is finite. Therefore, this division makes sense. And we can do this on both sides of this equation. So we have this equation with these pi's, probabilities. That is the stationary distribution, or at least one. that exists when you have irreducibility and positive recurrence. We used positive recurrence pretty explicitly. Irreducibility, I should have said as we were going through it, I did make assumptions that I can get from something to something. That's sort of in my proof. We did need irreducibility as well. And that's it. That's it. For the goal of proving just this part of theorem pi 2, we are done. That proof wasn't as bad as I thought it was going to be or as tedious as I thought it was going to be, but I promise you it's going to get worse. So here would be another point that you might want to exit this video, because again, I don't want you to lose your enthusiasm for this course by getting bogged down in tedious stuff. The next thing I want to do in the remaining time is head towards proving theorem pi 1. I will eventually come back to proving the rest of theorem pi 2. But I'm going to go to theorem pi 1 now. Why did I prove that piece of theorem pi 2? Check out theorem pi 1. For an irreducible, positive recurrent aperiodic Markov chain, I claim this limit here exists and is independent of I. And with irreducibility and positive recurrence alone, we know by theorem pi 2 that a stationary distribution exists. And I want to use this fact in the proof of theorem pi 1. So that's why I went and proved that little piece so it can use it for pi 1, the pi 1 proof. And we're going to prove this next. Although it's not going to make it into this video, I have some lemmas to talk about for the remainder of this video. First off, a claim that I will not prove. And I don't like not proving things, but this is really a huge aside into number theory. This claim is, I would call, a generalization of something known as Bézout's identity. Usually you see Bézout's, well, I'll tell you at the end how what you would usually see. So let me just state my claim. I'm going to let A be a set of integers, and I'm going to let D be the greatest common divisor of the elements in A. So I claim, or Bézout claimed, that there are elements, little a1, little a2, up through little am in A, and there are integers, little c1, little c2, up through little cm, and these integers could be positive or negative, such that if you use these integers as coefficients on a linear combination of these elements in A, you can get this greatest common divisor D. Bézout's identity is usually just two numbers, not m numbers, and usually doesn't have a set at all. So it's usually, suppose A and B are integers and D is the greatest common divisor of A and B, then you can find two integers such that if you make a linear combination out of A and B with those integers, you can get that greatest common divisor. That's why this is a generalization. Unfortunately, I'm going to leave that there. Actually, fortunately, I hate proving this. I hate proving this, but it's definitely way off in left field for us. And we are so far away from getting to where I want us to be. So next up, a lemma for proving theorem pi 1. And I think I have time to prove this lemma, and that's where this video is going to end. So here's my lemma. Let's go back to a Markov chain and stochastic stuff, because we didn't have anything Markov or any probability in Bézout's identity or Bézout's theorem. If state I has period 1, then there is a number, capital N, such that I can go from I to I in little n steps with positive probability for all little n greater than or equal to n. Right? You might have a state with period 1 where you could return in 3 steps and you could return in 7 steps. But I'm claiming that if you take really high powers of your transition matrix, the diagonal entry in the ith position will always be greater than 0 after a point. To prove this, I'm going to start out by assuming I have a state I with period 1. I'm going to define a set, A sub I, to be all n such that the probability that I can go from I to I in n steps is greater than 0. N here is going to be greater than or equal to 1. Certainly no negative values when we're talking about transitioning in a certain number of steps. Now, because I has period 1, the definition here of period is the greatest common divisor of numbers in this set. So I know that the greatest common divisor of numbers in this set AI is 1 by definition of state I having period 1. I'm going to prove this result in 2 steps. Step 1, I'm going to show that AI is going to contain 2 consecutive integers. And then step 2, I'm going to try to convince you that that's going to give us the result that we want. So let's prove step 1. The greatest common divisor of all the elements in AI is 1. So by Bezout's identity, we know that there exists little a1 through little am for some m, at least 2, m is greater than or equal to 2, in AI, and integers little c1 through little cm, such that this linear combination is equal to 1. By the way, these integers are going to have some positives and some negatives. There's no way, everything in AI right now is greater than or equal to 1. We're counting the numbers of steps you can possibly return to a state I in. So maybe 1 step or 2 steps. When we compute period of a state, we're not including the fact that you can return in 0 steps. So we're taking integer values greater than or equal to 1. But these integer coefficients are certainly, we're going to have some be negative, or we're never going to get this linear combination of integers greater than or equal to 1 using integer coefficients. There's no fractional coefficients. So the only way to get this sum down to 1, if you will, is to have some of these c's positive and some negative. So let's let j be the number of positive c coefficients here, and k be the number of negative coefficients. There are m terms, so j plus k is going to equal m. I'm debating how technical I want to get into this part. I think it might be easier to not get so technical. Let me try it and then try to clarify it. There are some positive coefficients and some negative coefficients, again, j and k respectively. I'm going to let little I sub 1, little I sub 2, up through little I sub j be the indices for the terms here that have coefficients that are positive. So if this C1 is negative, but C2 is positive, then little I1 is going to pick up that index. Little I1 is going to be 2. And then I'm going to let the rest of the indices, so little I sub j plus 1, little I sub j plus 2, up through little I sub j plus k, which is going to be I sub m. I'm going to let those be the indices for which the corresponding C coefficients are negative. Okay, so I am going to move everything with negative coefficients to the right-hand side here. What I'm going to get is something that looks like this. Here's my positive coefficients, my Ci1 through Cij. And over here, I rewrote my C's as B's, because really this would be a negative C. These B's are the negative of the corresponding C's. So these C's over here are positive. These B's are the negative of negatives and are all positive. See, I'm not sure that was worth it. So if that didn't make sense, let's go back to the original sum. Let's just suppose that the positive coefficients were up front. You could reorder things and reindex things, but I'm trying to make this simpler and not reindex things. If these are the positive coefficients and these are the negatives, I'm moving all this to the right side. And then those will have negatives in front of them. And these coefficients will then be positive, if that makes sense. I don't know if that made it better or worse, but let's persevere. I did say tedious. So note that any positive, meaning positive coefficient, linear combination of elements in AI are again in AI. For example, suppose that the numbers 3 and 7 are in the set AI. What that means is I can go from I to I in 3 steps with positive probability, and I can do it in 7 steps with positive probability. Just to make sure you're aware, going from I to I in 3 steps, this probability does not preclude us having visited I in between those 3 steps, right? These are not first return time probabilities at all. So if we assume both of these are positive probabilities, i.e. we took the number 3 out of AI and 7 out of AI, then I can return, starting at I, to I in, say, 2 times 3 plus 5 times 7 steps. Because starting at I can return in 3 steps. I can do that again in 3 steps. Now I can take a route that takes me back in 7 steps and repeat that 4 more times. And so we can return in 2 times 3 plus 5 times 7 steps with positive probability. This is what I mean when I say positive meaning positive coefficient linear combinations of elements in AI are in AI. Well, these A's up here are from AI. These are positive coefficients. So this is an integer, given that the AI values were integer values and the C's were chosen from integers. This is an integer in AI. It's a positive linear combination of elements in AI. This one, too. These are from AI. These are positive integers. This is a positive linear combination of elements in AI. This is in AI. Here is an integer in AI. Here is one in AI. This one is one more than this one. That's what I was trying to show for step 1. I was trying to convince you that AI contains 2 consecutive integers, at least one time. And here they are. Okay, so here's what we're trying to prove. This was our setup. Step 1 done. In the remaining time, I want to tell you why step 1 is going to get us this final result here. We know there are 2 consecutive elements in AI. I'm going to call them not CI1A1 plus, simply K and K plus 1. So if K and K plus 1 are in AI, then 2K, 2K plus 1, and 2K plus 2 are in AI. We can get 2K in AI if we can show that starting at I, we can return with positive probability in 2K steps. I already know that K is in AI, so starting at I can return in K steps, and I could do that again. And that corresponds to a path starting at I, where we can return in 2K steps. If I can return in K plus 1 steps, and I can return in K steps, why don't I do that? I'm going to return in K steps, and then return in K plus 1 steps for a total of 2K plus 1 steps. I can do that with positive probability, therefore 2K plus 1 is in AI if K and K plus 1 are. If I can return in K plus 1 steps, then I could do that once, and I can do that again for a total of K plus 1 plus K plus 1, or 2K plus 2 steps. So these values are in AI if these are. So if all of these are in AI, then I know that 3K, 3K plus 1, 3K plus 2, and 3K plus 3 are. We can get all of these path lengths out of these path lengths as possible ways to return to I with positive probability, and there aren't even unique ways. So for example, this 3K plus 1 might have come from this 2K plus 1 and another K here. It might come from 2 of these and another K plus 1. Convince yourself that you can get all of these numbers from these numbers, and that may not be unique. There may be multiple ways to get these numbers out of these numbers. Similarly, if we can get from I to I in K and K plus 1 steps, and 2K, 2K plus 1, 2K plus 2, and 3K, 3K plus 1, 3K plus 2, 3K plus 3, we know that we can get from I to I with positive probability in 4K steps, 4K plus 1, 4K plus 2, 4K plus 3, and 4K plus 4. Therefore, these numbers are in AI. Let me just pick one out here. 4K plus 2 might be us going in 2K plus 2 steps, and then returning again in another K, and then another K, something like that. So that would be a total of 4Ks plus 2. Again, that's not the only way to do that with the numbers that have come before. So this is sort of a proof by ... But we can continue, and we can show that for any positive integer j, we can return in jk steps, jk plus 1, jk plus 2, out through jk plus j. This is j equals 1, this is j equals 2, this is j equals 3, this is j equals 4, and we can keep showing this for j equals 5, 6, and 7, and so on. And in each case, we get a sequence of numbers included in AI. I claim that when j is greater than or equal to k minus 1, these sequences of numbers included in AI will start to overlap and will continue to overlap. And I'm almost out of time. I would convince myself by writing out a few more of these sequences. Pick a fixed k and start writing this out, and convince yourself that you're going to get these sequences of numbers included in AI, and eventually they will overlap and you'll never miss any, leaving no gap in the sequences of consecutive integers included in AI after that point. This is what we wanted to show. We wanted to show that there is some positive probability of moving from I to I in n steps for all n after a point. because AI was the set of numbers for which we get these positive probabilities. So I guess rather than writing this specific capital N, I could write something that depends on this J and K, but the point is the same. Eventually, when you go large enough, you will always find the possible numbers that you can return in with positive probability in A, which means you will always be able to return to I with positive probability for some large integer and all integers after that. I told you it was tedious. Even then, I did a little bit of, I wouldn't say hand waving, but some ... in my proofs, which we could easily write out formally, but I don't think it adds anything to the proof. I am definitely out of time now. We have not proven theorem pi 1. In my next video, I think I'm going to do that and get to proving part of theorem pi 2. I do not want to lose you and your interest. So my next video is going to be in the numbering of my videos, kind of an appendix or maybe a part B to this, so that it's really easily skippable to people in the future who are watching this when the series is done. But I will let you know when we're back to the interesting stuff, which is first step analysis for Markov chains. It is awesome and powerful. You're going to love it. I hope to see you there.